Language translation model advances and challenges. Recent developments in translation models highlight a shift towards specialized, context-aligned approaches. Next Rosetta stands out as a versatile collection of translation models designed specifically for structured data in JSON format, supporting a wide array of languages and built on top of Gemma 3 or GPT-OSS architectures. In benchmarking, it has outperformed closed-source competitors like IA Expanse in Blue and F++ scores, though fell slightly short on metric X24, underlining the ongoing importance of nuanced task-specific metrics. User feedback reveals that Rosetta models deliver reliable results for technical and general-purpose texts, but can struggle with creative or narrative-rich passages, particularly in English to Korean translation, where nuance and idiom trip up even the largest 20B parameter models. This underscores a persistent challenge in translation AIs. General domain capability is not a guarantee of creative language fidelity. Interestingly, users found that rephrasing prompts, such as changing JSON keys from text to narration, improves translation quality for role-playing text, a subtle reminder that prompt design remains critical in LLM-based applications. Beyond raw translation, the workflow around LLM deployment shows increasing maturity. Users reported issues with converting models to GGUF format for local inference and handling different float precisions, demonstrating both the rapid, community-driven innovation in quantization and the pain points of open infrastructure. Feedback loops between model providers and users remain essential as translation models are pressed into production roles where both correctness and context sensitivity are essential. Training, quantization, and local inference. The explosion of open-source LLMs has fueled democratization, but has also exposed the substantial technical divides in both training and local deployment. Guides like the recent GRPO plus TRL script for Windows, enabling group-relative PPO fine-tuning with verifiable rewards, LoRa, and 4-bit quantization, eliminate the traditional dependency on Linux or Colab, opening up reinforcement learning-based model improvement to a much broader audience operating on consumer-grade GPUs. However, actual hardware barriers remain substantial. The community discussion around running Qwen 3 models, e.g. Qwen 3 Thinking 235B, Qwen 3 Coder 480B, in editors like continue.dev, illustrates that although high token limits are supported in theory, performance rapidly collapses on all but the largest multi-GPU server stacks. Practical advice surfaces repeatedly. Stay within the 14B, 32B model range for responsivity unless you have enterprise-class hardware. Token context windows mean little if your setup can't physically feed them fast enough. Compatibility quirks also abound. AMD users, for example, find that Polaris-class, RX 570, GFX 83 GPUs are not properly supported by many tooling stacks, e.g. Ultima, despite theoretical ROP compatibility. Alternatives like LM Studio or direct use of Llama.cpp's Vulkan backend offer partial workarounds, but showcase the ongoing fragmentation of AI hardware support, especially for those outside the NVIDIA ecosystem. At the same time, new model releases demonstrate how quickly technical ceilings are rising. NVIDIA's Nemotron Nano 12B V2 base, a 12.3B parameter hybrid Mamba 2 transformer LLM, supports a 128K token window and is trained on a sweeping corpus that includes 3.5T tokens of synthetic data and over 900B tokens of code across 43 programming languages. It performs at or above its peers in established benchmarks, e.g. MMLA 78.24, Human EvalSat 1 6103, GSM 8K COT 91.66, evidencing the compounding benefits of model scaling, multilingual data, and synthetic QA for both coding and general reasoning. Meanwhile, models like Huihuai GPT OSS 20B BF16 abliterated, an uncensored derivative with refusals removed, highlight the persistent tension between uncensored performance and safety filtering. As safeguards drop, user responsibility and legal risk rise, a trade-off now familiar to those deploying local LLMs. Hardware and systems, cloud, local, and kernel innovations. Database system reliability is a perennial challenge, now increasingly solved via cloud-native features. Chroma's Wall 3, an open-source object storage native write-ahead log system, builds on S3's new atomic conditional rights, if match, if none match, to deliver lock-free durability without complex disk fleet oversight or cluster-level routing. By leveraging per-collection logs, stateless nodes, and innovative log audit checksums set sum, Wall 3 achieves durability, scalability, and ongoing provable safety with a fraction of the operational burden of Kafka or even modern event streamers like WarpStream. On the inference side, hardware-efficient matrix multiplication, GEM, kernels are still a battleground for AI speed. LiquidGem's new W4A8 kernel, optimized for serving large LLMs, brings high throughput for INT-FP mixed precision operations, helping maintain top-end performance. Interestingly, QServe, an older method from the SVD Quant team, is reportedly still competitive in certain contexts. A reminder that in AI infra, last year's outdated optimization is often good enough, depending on workload and cost. Further accelerating efficient LLM training, FlashRL brings a plug-and-play framework for generating RL rollouts in INT8 and FP8, weighing accuracy against performance, particularly for large models, 14B+, and complex reasoning tasks where quantization overhead is offset by faster scaling. Hybrid generation is also supported, letting some data parallel workers operate in higher precision, BF16, while others stick to low precision, further closing the gap between model fidelity and throughput. These underlying improvements are rapidly manifesting in front-end capabilities. For instance, local retrieval augmented generation, RAG, using Ollama, now benefits from improved embedding chunking via LLM-based segmentation, boosting semantic retrieval, albeit at the cost of more GPU compute. Integration with Hugging Face's embedding models is a work in progress, with tools like NPCPY and NPC-SH helping bridge the functionality gap for custom flows. Cognitive AI, LLM embeddings, and human brain alignment. An intriguing development at the interface of neuroscience and AI is the strong empirical alignment between the way LLMs represent scene captions and how the human brain encodes natural visual scenes at higher cognitive levels. Functional MRI data reveal that high-level visual cortex activity can be robustly predicted using MPNet and similar LLM embeddings of scene descriptions, outperforming traditional bag-of-words or object label models not only at the group level, but even when mapping representations between individuals. Using representational similarity analysis and voxel-wise linear encoding, researchers demonstrate that LLM embeddings, derived purely from descriptive text, successfully mirror the semantic structure and region-selective tuning, e.g., face, place, food areas, observed in the brain. Decoding analyses go even further, reconstructing plausible scene captions from neural activity alone, with accuracy approaching that of multiple human annotators. Notably, AN models trained to map images directly to LLM embedding space align more closely with visual cortex signals than even state-of-the-art image-text models trained on web-scale data. The practical implication, as LLMs become more central to cognitive modeling of scene understanding, their high-dimensional semantic spaces offer a new formalism for quantifying and comparing the richness of human perceptual encoding, potentially giving rise to fresh approaches in brain-machine interfaces and the science of perception. Automation and agent architectures. From health records to coding AI, the push for reliable task-specific AI agents continues across domains, with an increasing focus on trustworthiness, a theme especially critical in health and software engineering. In the medical field, a recent study advances the state of LLM-based clinical agents by introducing TrustAgent, which supplements standard reasoning modules with fine-grained stepwise confidence estimation and explicit abstention when uncertainty is high. The novel HCAT-KCENT metric quantifies not just overall accuracy, but the ability of the agent to provide reliable answers under strict safety constraints. The results are striking. Traditional agents fail utterly under high reliability thresholds, HCAT 70%, while TrustER agent maintains useful accuracy, revealing the hidden cost of neglecting abstention in high-risk settings like EHR-based QA. Elsewhere, infrastructure advances for agent automation gain ground. The Meganex 3.0 project reimagines agent-based execution around resilient, self-auditing architectures that enforce a plan-critic repair feedback loop, not just through prompt engineering, but via core agent logic. This brain executor mode ensures that no action escapes internal scrutiny, highlighting how mature agent design increasingly blurs the lines between prompt code logic and automated safety. Tool integration remains a defining challenge. Open-source solutions like the Skipper tool allow Claude Code to control desktop actions programmatically, a double-edged sword that shows the practical utility of LLMs as general agent backends, but reminds us of the real, and sometimes glaring, security trade-offs inherent in broad system automation. The agent ecosystem in coding is equally dynamic. By orchestrating multi-agent frameworks with explicit context stores and task delegation, projects like Multi-Agent Coder can outperform commercial coding copilots, e.g. Claude Code, on competitive leaderboards like Terminal Bench. Crucially, gains are not just due to raw model quality, but to the framework's intelligent use of specialization, persistent knowledge artifacts, and prompt-driven trust control, underscoring that leading-edge coding agents succeed by pairing model families, e.g. Sonnet 4 vs. Qwen 3 Coder 480B, with architectural finesse and tailored evaluation harnesses. These lessons, quantitative uncertainty estimation, model-agnostic tool orchestration, and safety at every step, are converging on a blueprint for trustworthy agents across verticals. GUI, vision, and robotics, new applications and real-world integration. Cutting-edge applications are pushing LLMs and vision models well beyond the text box. UI Venus sets a new state-of-the-art for GUI navigation by training on 350K annotated samples and leveraging reinforcement fine-tuning for precise action-level reward design. The model achieves top scores on benchmarks like ScreenSpot Pro, 61.9 EMB, Android Control, and GUI Odyssey, not just grounding UI elements from screenshots, but navigating cross-platform interfaces and adapting to ambiguous user intent. Data quality is a recurring theme. UI Venus's superior performance is attributed not just to architecture, but also to systematic cleaning, clarifying user intent, correcting redundant actions, and synthesizing missing steps with LLM-augmented modeling, proving once again that AI's effectiveness is routinely capped by the quality of input and annotation. Vision pipelines, meanwhile, are becoming modular and user-driven. The stand-in preprocessor for Comfy UI, for instance, is a required component for unlocking the identity-preserving performance of the stand-in pipeline, emphasizing community concern over consistent workflow logic in image-based generation. Finally, robotics hardware is increasingly accessible for creative prototyping. A notable example is a canoe retrofitted with Piper robot arms, programmed in ROS and controlled via joystick. By mapping paddle dynamics to a differential drive, similar to tank steering, the platform demonstrates non-destructive, real-world robot integration with a design that also allows for easy expansion, potentially to full autonomy. The intersection of careful hardware design, creative modeling, and open software, ROS, 3D scanning, modular brackets, signals a new era for both hobbyist and applied robotics experimentation.